Okay, presentation of the VHF group today. Factors influencing F-layer propagation at 50 megs as solar cycle 25 peaks. Yeah. Right. All life on 6 meters begins with our sun. To give you a roadmap. Then we'll look at surprises of the solar cycles, the sun's influence on our ionosphere. That's triply important. Winter is not always discontenting, to paraphrase Shakespeare. Mindfulness, path elevation and antennas. The importance of azimuth. Opportunities from precursors. So, the solar cycle. The big question, of course, in everybody's mind these past few weeks and right now is, are we there yet? Well, looking at where we've been, and this graphic from the Royal Observatory of Belgium, which is a world data centre for everything solar and solar cycle. When you look at that, you think, oh dear, is there a trend in here? And does it look like that? Well, for the past couple of decades, everybody seems to think so. At this point, I might point out that 44 years ago, I wrote an article in conjunction with my previous boss at the Space Weather Services, Leo McNamara, or Dr. Leo McNamara. And it said, it was published in Amateur Radio Magazine and other places, and the title was, Kiss Your Last Big Sunspot Maxima Goodbye. Well, that of course was between after 1980, so it didn't happen, did it? We were wrong. So, where are we? This is sort of like the progression as we go over the last dozen years. So the greeny yellow spiky one is the daily sunspot number. The smoothed monthly sunspot number is the blue spiky one. And the monthly the monthly sunspot number, and then the smoothed monthly sunspot number is the red one underneath. Now the dashed lines there is some predictions. This is a group of scientists who get together and try to come to some sort of agreement about where it might be going or not. So, solar minimum, that's when the solar cycle starts. It began in December 2019 with a smooth sunspot number of 1.8. Nothing like where we're at the moment. The 2024 forecast for April to July from the Space Weather Services is between 142.9 to 147.9. A mere 5 in 140. That's not much. So what's been happening over the year? Here we are up until September. October hasn't finished yet. And the numbers are sort of like well ahead of what you see from the forecast in the bottom line. So the actual observed sunspot numbers are exceeding forecast regularly. In fact, we've exceeded solar cycle 24 numbers for more than the last 12 months. So, comparing solar cycle 24 with 25 so far, what does it look like? Well, it looks very interesting indeed. We go back to 2023, and we were already above the forecast. And the smooth numbers have travelled on and on well above the forecast, well above solar cycle 24. Now that's very encouraging. No wonder 6 metres is going nuts. So that's what it looks like in a smooth sense. So what happens? Circulation in the ionosphere. This is very important when we have to consider what happens month to month, day to day, week to week. Here's a sort of a general diagram of what's happening in the atmosphere way above our heads. Solar radiation coming in from the lower left there expands the atmosphere and ionises, well, weakly ionises the upper atmosphere. And in heating the atmosphere, it generates a thermal tide, which moves in every direction away from directly below the sun's point on the earth. So you get winds from the solar cap also get pushed out of the way by this thermal tide, and so you get this complex circulation through the atmosphere. So solar radiation drives the global thermal tide. Winds, thermospheric winds from polar cap processes, excite planetary waves, that is, increases in density and pressure, with periods ranging between 2 to 16 days, so that generally 2, 5, 10 and 16 days. And this mixes the atmosphere and the ionosphere. You get gravity, or what they call gravity waves, which are really buoyancy. I mean, if you throw a football on top of a pond, the waves you get driven up to start with then get pulled down by gravity. So that's why they're called, in a crude sense, gravity waves.
Doesn't relate to that Dubas article.
What?
That Dubas article on gravity waves. It's different about the very slow changing.
I don't fully recall. Sorry?
About a year ago.
Which is the reason why I don't fully recall. I should have begun to say that if you have any questions as I'm proceeding, don't hesitate to ask. So, in a sense, the ionosphere is blowing in the wind, to paraphrase Bob Dylan. So, as you can sense, season is a factor. And so far as 6 metres an F2 propagation is concerned, there's this thing called the winter anomaly. And when you run a prediction of the MUF over a distance of, say, 4,000 kilometres, which was pretty much tangential, and it's the sort of maximum hop you can get from the F2 region. For a sunspot number, low sunspot numbers, say around 10, the blue line gives you some idea. It's pretty smooth throughout the year. Whereas if it's 100 or above, you get this lump in the middle, which is a very interesting thing and counterintuitive. And if you look at the 50 megs level there at the top of the chart, you see there's a period over winter in which you're likely to get an MUF above 50 megs. Doesn't mean to say it's going to happen every day. So, solar activity is a factor here, the sunspot number. If it goes to 180, the graph moves upwards. Brilliant. so much the better. So we're in this, well, in the Northern Hemisphere, is this sort of territory at the moment. And that expands the months that likely propagation might be available.
F2 layers are always about the same altitude.
No, that goes up and down daily with the thermal tide, seasonally, so monthly, and throughout the year.
So it's like racing cockroaches.
Yes. So if we're looking at a 4,000 kilometre path like this, the ray path is very low. As I said, pretty much tangential. Scales are exaggerated for the purpose of illustration. More about the winter anomaly. Let's summarise that. 4,000 kilometre path, mid-latitudes in the Northern Hemisphere, path elevation, tangential. Why does that happen? Well, in the winter, you get more oxygen ions relative to nitrogen ions. The oxygen is lighter than the nitrogen, so there's more, and they're more easily ionised, so there's more available. So hence, that increases during the winter. So you get seasonal circulation because of that. With the sunspot number from 100 plus, 6 metres F2 may open over autumn, winter, spring. At the mid-latitudes, for the graphs that I showed you previously, transatlantic, trans-Mediterranean, trans-East Asian and trans-Pacific. So what about the Southern Hemisphere? Well, you flip the graph sideways. And I've just done it for the sunspot number of 180 to avoid doubling up. Again, 4,000 kilometre path, mid-latitudes, Australasian, South Pacific regions. You can work VK6 from here. And out into the Pacific. So, in the Southern Hemisphere, autumn runs March to May and winter June to August. There's a small overlap with the Northern Hemisphere. Whoop-de-doo, late March, early April. Again, scales exaggerated for purpose of illustration. Now, another factor we need to consider. If you've got a tangential path like that, your antenna elevation lobes, the elevation of the lobes is important. As you can see, I've contrasted a 3-element Yagi 10 metres above ground and an 8-element Yagi 20 metres above ground. So down there at 1.8 degrees, the OA4TT's 8-element Yagi is losing about 6-7 dB, whereas the 3-element Yagi 10 metres above the ground loses rather more, probably 10 dB, so you only get 4.5 dBi gain. So 6 metre DX propagation paths are inherently low angle. That includes for sporadic E. Your antenna's working at the bottom of the first lobe. You've got to keep that in mind. Now, the next thing we need to consider is the equatorial ionospheric anomaly. That's a bit of a mouthful. So, if we look at the density of the ionosphere along a line running north and south, pick a latitude, you get a curve like this, where it peaks roughly 20 degrees geomagnetic latitude either side of the equator. This is an actual measurement and taken from an article of mine produced in the 1970s when I was working for the Space Weather Services. It used to be known as IPS. So ionisation builds up either side of the geomagnetic equator as the day progresses, because it drives electrons up from the equator until high in the F layer, and until they start to fall over north and south, and it's called the fountain effect for obvious reasons. And around the equinoxes, those two curves are pretty much symmetrical. One will be bigger, one will be smaller than the other outside of the equinoxes. But sometimes that's sufficient to get propagation when we need it. So when we look at it on a global basis, those isolines are the density of the ionosphere. And so you get these, here you see the two red streams. This is outside an equinox. But nevertheless, that's very dense. That's sufficient to support 6 metre propagation across them, north to south, and at an oblique angle. So solar radiation and ionospheric convection maintain the latitudinal extent. That was left to right on the map there. So production of the equatorial ionospheric anomaly follows the sun westward. Got to think about that time of day. So we come upon trans-equatorial propagation, in other words, across the equator. And by this we mean the geomagnetic equator. Here's the traditional diagram with equatorial anomaly north and south, and a couple of ray paths in there. Notice that it looks like there's some focusing of the signals with the two different paths. And the paths, of course, refract from one side across to the other without an intermediate ground reflection. So this is afternoon type or super mode TEP. Quarter lot propagation with ray paths focusing. North to south paths are typically 4,000 to 7,000 kilometres, and oblique paths 10,000 kilometres plus. So here's a diagram, again from that paper that I did back in the early 70s. This is a hand tracing from by a draftsman from a computer printout, and then it's been annotated. They're taken directly from measurements of the ionosphere along pretty much 150 degrees east latitude. So transmitted at Seoul in Korea, and the receiver, shall we say, down around Townsville there, you can see the ray paths coming together. This is why sometimes you can hear somebody to the north of you working the DX and you can't hear a damn thing. And the footprint it makes on the ground is not a circle or an ellipse. It looks a bit like the whoosh symbol by Nike. I've actually seen backscatter radar measurements which show that very dramatically. Taken from backscatter radar from Brisbane back in the 60s.
Roger, Seoul and Townsville are not the same latitude, are they? On longitude.
And longitude.
It's a north-south path.
It's a north-south path, but not quite orthogonal. I don't have what time of day that is.
The geomagnetic equator.
Yes, it's nearly orthogonal with the geomagnetic equator, which is pretty much north of and parallel to the geographic equator at these sorts of longitudes. It's not too far off orthogonal. So, as I described, I had personal experience following the focal point on foot. I spent some time in Townsville in the 70s working for IPS, now known as Space Weather Services, and two local amateurs living basically a street apart. The northernmost one could hear a really good signal on 6 metres, and could relay that on 2 metres just across the block. And the guy across the block could not hear that signal. And I could walk between the two stations and follow the wandering of that focal point. It damned extraordinary, it really was. So, further on transequatorial propagation, just to take a global look at orthogonal and oblique paths. This is pretty indicative of what's happening. We look at longitudinal EIA propagation. In other words, along the anomalies, you get these sorts of things. If the peak of the anomaly, either north or south, is of sufficient density, you get propagation along it. There is another mysterious off-direct path, a non-great circle path as well, which is known to refract from Australia to South America across there via the southern equatorial anomaly. So, there we go. So let's have a summary so far. Our opportunities and experiences are controlled by the sun. Well, duh. Solar cycle 25 may be peaking or yet to do so. Winter winds are winners. Ray path elevation is smaller than you think. Azimuth matters more than elevation. Development of the equatorial anomaly brings opportunities. The equinox is a good neighbour. So, are there any precursors? So, do lower frequency bands point you to MUF on 6 metres? Well, yes, in a strange way. Here's a backscatter scan from 30ER, or VK30E, 30ER, in VK, well, yeah. So this is a bistatic backscatter chirp radar, described in Dubis some years ago, and still regularly used. And this was taken on 28 megs in the 15th of May, and that big week of 6 metre propagation went nuts. Now the interesting thing is here you can see the first skip is pretty much conventional, 2250 kilometres. You get a second one at just under 5,000 kilometres, and then there's this pretty much nothing, just propagation noise, and then they backscatter at 42,000 kilometres. That's quite phenomenal, and the signal to noise ratio is around 12 dB. Guess what? Andrew worked W3XS on 6 metres in Idaho at the time this trace was taken. Now, What is it indicative of? It's indicative of a surprisingly uniform F2 layer. So 28 megs around the world propagation is a precursor. What happens there? Well, you can see the dense spot of the F layer or F region of the ionosphere. It has a peak, and the signal enters at a very shallow angle and is then sort of like conducted around, not exactly like a whispering gallery, but more like a guide. Waveguide, if you like. So how is that happening? Well, here's a complicated way to look at it. So at the right-hand side there, you see the radius RR, or R subscript R, is sort of where you're entering F2 max. If to the left, marked R, the radius at R, turns by a certain angle, then it will curve sufficiently to enter the F2 layer at a critical angle. So how does it come to do that? Well, the F1 layer deflects the ray path at a critical angle. These are studies from back in the 1950s, when Sputnik satellite 40 meg beacon was heard around while the satellite was below the horizon. Everybody wanted to know why it happened. Well, they worked it out. So with the F1 layer, daytime, between 4 and 5 megs at this sort of sunspot number, and its height around 90% of the base of the F2 layer, that might produce some nice critical angles to launch it around the world. So, no, F1 is below the F2 layer. No, it was in the FUF layer.
Oh, really?
Yeah. Look up the orbital. So it was around. I won't speculate again. So if we can determine the critical angle between where the F1 layer launches it, say for example there at that source, the angle beta only needs to be between quite a narrow range, but quite an achievable range, if you want to look at it that way. Here is the capability amid solar cycles, shall we say a sunspot number of 70 or 80. With a higher number, those graphs move upwards. So you get a better, it takes less of an angle to launch you into the F region at a critical angle. Of course, if it's lower, then they drop, and the range of angles becomes narrower. So, primary factors when on air. The solar flux index is your friend. With SFI between 120 and 150, you can pretty much see improving MUFs. Keep an eye on it. When it's between 150 and 200, you generally get excellent MUFs. 200 plus, it's pandemonium. At the same time, you've got to keep a close watch on the A and K indices. In other words, the geomagnetic indices. Low values, it's quiet times, so you can go hunt and pounce high values, you get geomagnetic storms, so you can return to your knitting. And it's the flux what brings the pleasure, but the flare's what brings the pain. So what about the future? Well, here is less than 10 days ago, NASA's solar flux index prediction for the next solar cycle. Now, we could be in for something more of the same or even better. Then again, if you're pessimistic, it could be worse. Or if you want to look at it in terms of solar cycle numbers, you can draw the same conclusions from here. Thank you.